Hi everyone, my name is Lucy. I'm currently completing my honours in environmental science at James Cook University under Dr. Jack Kochi, while also working part-time as a project officer in soil restoration at Southern Gulf NRM. My honours is also part-time, so it's about halfway for me at the moment. Today I'm going to be presenting an overview of my honours project, which falls under the Tropical North Queensland Drought Hub's collaborative projects titled Rapid Assessment of Mitchell Grass Tussock Density on Southern Gulf Rangelands using high-resolution drone imagery and machine learning. We ultimately want to use this approach to more efficiently and more accurately evaluate land condition of pastures to improve sustainable grazing land management and drought resilience. Before I get started, I'd just like to acknowledge the traditional owners of the land on which we conduct our work, the Wulgurukaba, Bindal, Wonamara and Irindali people. So this project is funded by Southern Gulf NRM, James Cook University and TNQ Drought Hub through funding provided by the Australian Government's Future Drought Fund. I would also like to mention that this project feeds into a broader project with Southern Gulf NRM, which is focused on evaluating the effectiveness of restoration methods on bare ground in the Southern Gulf region. Also, a really big thank you to all my supervisors and our team working on this project. So our study is situated in the Mitchell grass dominated rangelands of the Southern Gulf in northwest Queensland, specifically in the Mitchell Grass Downs grazing land type, shown here. There are 4 species of Mitchell grass. These are curly, bull, barley and hoop Mitchell, all 4 of which are included in the imagery for this study. These are native 3P grasses, so they're perennial, productive and palatable, which are not only a great source of forage for livestock, but also great for cycling nutrients and maintaining the structure of the soil. The amount and distribution of Mitchell grass tussocks is a really important indicator of land condition, also a really key factor for evaluating the effectiveness of restoration techniques on bare ground in this region. We are looking to find the individual tussock count of Mitchell grass using instance segmentation as a metric for measuring land condition of paddocks. I'll get into a little bit more detail on this later. So in rangeland production systems, accurate and consistent data on land condition is critical for decision making to ensure long-term sustainability, productivity and profitability, particularly in the face of variable climatic conditions. Here we have a few different approaches to assessing land condition. On one end we have an on-ground assessment called an LCAT. This is where a user will stand in a paddock and complete a survey which will produce a grazing land health condition rating from A to D, A being good, D being poor. This requires a detailed understanding of pasture identification, ecological principles, as well as an estimation of pasture biomass and vegetation cover. On the other end of the spectrum, we have sites such as long paddock or veg machine, and these will provide a report of broad scale cover of vegetated to bare ground at the property scale. So as you might expect, an LCAT is quite subjective to user experience, and the information provided from satellite-based remote sensing is often at 2/4 of a resolution to allow implementation of targeted management at the paddock scale. The increasing accessibility and adoption by NRM bodies, NGOs and landholders of lightweight and low-cost drones, coupled with advances in image classification procedures which use artificial intelligence, are opening the door to more efficient and reliable quantification of vegetation at spatial scales relevant for rangeland management. Such approaches, however, have not been rigorously tested in Mitchell grass dominated rangelands. So here we saw an opportunity to harness high-resolution drone imagery from our already ongoing projects with AI to more accurately measure tussock density. So this is an example of the same point in a paddock surveyed using 3 different methods: an on-ground LCAT, an above-ground drone survey, and what you can see from Google Earth, which my head's in the way, I can just realised. Now, we're not saying someone on the ground isn't valuable, it absolutely is, but developing this tool can be another additional support for broad-scale assessment to assist land managers. One thing to note is that there are significant trade-offs with time and the quality of information gathered here. So an LCAT might take 20 minutes and covers a small scale area in high detail. A drone will take more time but cover a larger area and at a higher resolution. And a quick look on Google Earth will show you a massive area with quite a low resolution. So the overarching aim of this project was to develop and test an approach to rapidly quantify the amount and distribution of tussocks in paddocks using high-resolution drone imagery and machine learning. Our first objective was to determine the ground sampling distance that are required to detect individual tussocks, so the different drone parameters. And our second objective was to work on developing an artificial neural network that was able to detect those individual tussocks. So here's just a brief overview of our field methodology. Firstly, we lay out ground control points and we survey these with an RTK GPS. This gives us the exact location of that point accurate to 1 to 3 centimeters, and we can use this later to georeference our images and create digital elevation models. Next, we fly our drone, which collects multiple images across our site. These are taken with an 80% vertical and horizontal overlap, which you can see here. Oh, there we go. And then we use a program called Agisoft Metashape, where we use a structure from motion with multi-view photogrammetry software to stitch these individual photos together, which creates these orthophoto mosaics. So these mosaics include those ground control points in the actual photo itself, and we add the coordinates from the RTK GPS, which allows us to georeference those mosaics and create really accurate digital elevation models. So for the first stages of annotating our images, we use the single images taken by the drone, split into 24 more manageable sized images, which you can kind of see behind my head, which made them a lot easier to label. So the two different images shown here are taken from two different ground sampling distances. We have one taken from 100 meters elevation and 25 meters elevation, or ground sampling distance above ground. So we've decided to focus on 25 meters GSD for this project, as it's a lot easier to distinguish individual tussocks, particularly during the dry season. There's a big resolution difference here between these two ground sampling distances, but this comes at the expense of time. So just for an example, we flew our drone over a 350 hectare site at 120 meters, and that took us almost 9 hours in pretty heavy winds. A 1 hectare area at the same height would take less than 5 minutes. So the lower you fly, the longer it's going to take you, but the resolution and quality of those images will be a lot higher. Also, for training a machine learning model, the quality of the images are very important. So at 100 meters, a tussock will be roughly 10 pixels in length, whereas at 25 meters, it might be upwards of 40 pixels, which is a much better image quality to train initially with. So now we've got these beautiful high resolution images of dry Mitchell grass tussocks. We have to figure out how do we make sense of all of this data. So just for a brief background, AI, which is artificial intelligence, is the umbrella term for all things machine learning, which then goes further into deep learning, which is inspired by the structure of our neurons in the brain to solve complex data problems. Image classification and instance segmentation are two distinct computer vision tasks which come under deep learning. So image classification will categorize the entire image into a class, such as giraffe, or in our case, Mitchell grass tussock, but it doesn't specify their locations and it has its overlap. Whereas instance segmentation will not only categorize the object, but it distinguishes each instance from the same class. So in our case, for a photo with multiple tussocks, image classification will label it as Mitchell grass tussock, whereas instance segmentation provides unique labels for each tussock, allowing for that precise counting, which is what we want to do to assess land condition. So we are very lucky to be partnering with Maxis AI for this project. This has really helped us automate the identification of individual tussocks and speed up the information extraction and reduce human effort. I'm running out of a little bit of time to go into all of the AI details, but in essence, we upload our images to the machine, we manually annotate each tussock, so drawing around each one, and this teaches the machine to ID tussocks. Then we train the machine on a new set of unseen images and validate how many it gets right and how many it gets wrong. We trial it again on a new set of images until we get to a point where Mitchell grass is predicted at an 80% confidence level. So that's it thinking I'm 80% sure that that's a Mitchell grass tussock. We can then pull a variety of information from this trained model, like parameters such as tussock count and density, which can then be used to quantify land condition. So as of a month ago, we have fed the machine 585 images, which included just over 11,000 annotated instances of Mitchell grass tussocks. We then evaluated that on a new set of images, which included 3,600 tussocks, and the machine was able to identify just over 3,000 of them. So at that point, it was currently under predicting by 16%. So with more evaluating of new images this past month, we've noticed an increase in the confidence required to identify these tussocks, and we hope to see that improve. So just a reminder, when I say confidence, this means that the machine is thinking, I'm 20% certain that's a tussock. This video here shows the confidence increasing on this slidey bar, like increasing and decreasing. So on our poor condition land, we noticed that the machine has a lot higher confidence at tussock identification. So it can identify all tussocks at 50% confidence, whereas on good condition land, it identifies all tussocks at around 20% confidence. So we hope to improve this by annotating more images of good condition land. Ultimately, our end goal for this project will allow landholders and researchers and NRM bodies to fly a drone across a paddock, capturing high resolution information, feed this data into Maxis AI, which will correctly identify Mitchellgrass tussocks, and you'll be able to pull out information such as land condition of pastures, tussock count and density. This will also help to assist landholders with sustainable grazing land management, which will ultimately improve the drought resilience of these landscapes in the process. I just realised I've added any questions, but I'm not actually there. So if you have any questions, feel free to email me. But otherwise, thank you for listening.